So now let's switch back to the slides. So just now we were proving this theorem, the independent set is equivalent to vertex cover, right? So we basically went through the same argument as the slides showing here, but because we sort of need some figures to illustrate the idea, so we were using the whiteboard, right? So now let's move to a second problem, right? So we were talking about the vertex cover, independent set, and now we move to the set cover, right? So we are going to talk a lot about the different problems in the next few lectures, and then try to just establish the equivalence between all these problems, right? So we are not really giving any algorithms for any of the problems. We're just saying that, well, if we can solve vertex cover, we can solve independent set, and vice versa, right? So now, let's move to a set cover problem. And the set cover problem, as the name suggests, it's highly related to the vertex cover, right? So let's just move to the definition, right? In the set cover problem, we are given a set of universe of elements and a collection of subsets of U and an integer k, and we want to know that are there at most k sub of these subsets. When we take the union of these subsets, it's equal to U, right? So it's a bit abstract, so let's just look into the example, right? So in this example, there's a universe set, right? This universe set is a pretty giant set, right? So in this example, it has 7 elements, right? So these are really just the total number of elements we ever care about in this particular instance of set cover. And this is the universe, and then we would have a collection of subsets of U, right? So I have a set of subsets, right? So the A, B, C, D, E, F are all the subsets of U, right? So basically I have multiple subsets of U. Like the first subset, let's call that SA, and SA consists of 3 and 7, right? Just notice that all these numbers are really just the numbers that appears in U, right? So my goal, right? So now I have SA, SB, SC, SD, SE, and SF, right? So my goal is really just to choose a subset of them, right? So I'm going not a subset of them. So let me just repeat what I'm talking, right? So let me just repeat, right? We have a universe and a subset, a collection of subsets, right? So SA and SA, SB, SC, SD, SE, SF, right? So these are all the subsets, right? So SA corresponds to 3 and 7, and all these elements appear in the universe set, right? So my goal is to be able to select a subset, some of these subsets, let's say SA and SC and SD, and such that when I take the union of this subset, SC and SD, then when I take the union of this subset, then everything inside this universe is covered, right? So in case we choose the collection of subsets that has this property, we call this a set cover. Right? So basically, I do want to find a collection of subsets such that when we take the union, it covers everything in U, right? So let's also be more concrete and just give you an application scenario so that it becomes more comprehensible, right? So so this would be just the sample application, right? So assume that there are m let's say, how can I say this one? All right, so assume that we really want to buy a subset of 6. So let me see how can I just deliver this message here, right? So assume that we want to install software in your computer, and assume that you buy a computer because you want to be able to do 7 things: 1, 2, 3, 4, 5, 6, 7, right? So these are all 7 different things you want to be able to do by using your computers. Now, there are a collection of softwares that are available, right? So the software name is called A, B, C, D, E, F, right? So SA would be the software A, and SB would be the software B, and so on and so forth, right? And here, the idea is that each of the software is able to perform certain jobs that you want to do, right? So maybe the first one will be the editing, second one will be the presentation, third one will be the programming, right? Something like that, right? So now the SA, right? So you can think that as a software 1, software A. Software A is able to provide two different types of services, right? The service type 3 and service type 7, right? So maybe it's able to tell you, provide a service of allowing you to do the programming and also allowing you to play some simple games, right? So this is the software A. And similarly, right, there are other software. Software B is only allows you to perform service 2 and service 4, right? And that's true for every single software, right? So now you really want to install a set of softwares so that after I install all the softwares, I'm able to do all these 7 things, right? So effectively, I'm going to pick up, and then I want to pick up a subset of softwares, right? So in this case, in the case that's shown in the example, I'm going to pick up the software C and software F, right? So after I pick up these two softwares, I install them, and then I look at all the functionalities these two softwares are able to perform. Then I sort of notice that actually I'm happy because I'm able to perform all the jobs I want to do, right? So that's the reason that we call C and F the set cover, right? So for whatever subset of softwares, when after I install all these softwares, I'm happy, I'm able to perform all these 7 types of jobs. These subsets would be called set cover. And our goal here is to be able to find, of course, find the minimum set cover, right? So intuitively, we really just want to be able to install as few software package as possible, right? So basically, that means that in general, we want to be able to minimize the set cover. That in other words, we want to be able to find the one set cover that minimize the number of minimize its own cardinalities, right? Cardinality would really just be the number of elements within the set, right? So now this is the optimization problem, right? And in order to really just make the output consistent, right? We saw sometimes people just turn that into a decision version of the problem, as I mentioned just now, right? So when we talk about the decision version of the problem, we ask that whether there are any whether it's true that the minimum subset has cardinality at most k, right? So this is the really just the whether it is true that the minimum set cover has cardinality at most k, right? So this is equivalent to ask this question, right? So again, as I mentioned just now, that if we are able to solve the decision version of the problem, we are able to effectively solve the optimization of the problem, right? So so now let's look into the quiz, right? So given the universe U equal to 1 up to 7 and following the set, right? So we want to say what is the minimum size of the set cover, right? So is it possible to just install one software that covers all the functionalities I want to use, right? It's obvious that there's no such software that can do all 7 things together, right? So A is wrong. And second thing is that just now we saw so that if I just pick up C and F, right? C and F, and then these two together, when I take the union, it's 1, 2, 3, 4, 5, 6, right? So 1 comes from here, 2 comes from here, 3 comes from here, also here, right? 4 comes from here, 5 comes from here, and 6 comes from here, right? So when I take the union, I cover everything, right? So 2 is a feasible solution, right? 3 is also correct, right? So the answer is 2, right? So our rationale is that 1 is impossible and 2 is possible, right? So basically 2 is the minimum size of the set cover here, right? So this is really just a simple exercise that helps you to internalize the definition of the set cover problem, right? So our next reduction exercise is to show that vertex cover is actually easier than set cover, right? So we sort of want to establish that if I am able to have a solver for set cover, then I'm able to solve the instance of the vertex cover, right? So given a graph and you want to solve the vertex cover problem, I'm able to reduce this graph to a set cover instance, feed that to the solver, and get the output, and then manipulate a little bit, and then we will get our true output. So assume that there's a good solver for the set cover, we are able to build we need to build an algorithm that uses the solver to solve the vertex cover problem, right? So this is what the theorem is talking about, right? So now let's just switch to the whiteboard and try to deliver the intuitions here, like why the vertex cover is reducible to the set cover or is simpler to the set cover. So now let's use the whiteboard to highlight the reduction process, right? So recall that we want to be able to reduce the vertex cover to the set cover. Right. So now we sort of start. So in this process, this reduction, we start with a graph, right? Let me just erase that and draw something that's consistent with the lecture notes, right? So we start with a graph. Our goal is to be able to find a subset of vertices such that it covers all the edges, right? So this is our input, right? And as I mentioned just now, I'm given a solver for the set cover, and I want to translate this as a set cover problem, right? The set cover problem. And after I translate that into set cover problem, I use the solver, and then I get an either yes and no answer, right? So yes and no answer is really corresponds to the decision version of the problem. Does that so the decision version basically asks that can I find the vertex cover whose size is at most k, or can I find the set cover whose size is at most k, right? So those are the decision problem, right? So now we sort of the center part of the reduction is really to compile an instance of the vertex cover down to a instance of the set cover, right? So basically, we want to do a transformation from vertex cover instance to set cover instances, right? So also recall that like the syntax of the set cover is that I need to articulate the vertex, the universe, and then define a number of sets, and then we need to let the run algorithm to the set cover solver to solve the instance we produced, and then we want to use the output of the set cover in order to determine the output of our original problems, right? So now, how do we determine the universe here, right? So we sort of want to cover all the edges here, right? So this is the very high level intuition of the vertex cover problem, right? So basically, naturally that we do want to be able to cover all the edges. So E2, E3, E4, E5, E6, E7s, right? So I'm just writing down or giving the name to each of the edges, right? So intuitively, right? So we sort of want to cover all these things, right? So that means that probably we can set our universe to be E1, E2, all the way to E7, right? Right. So now this is really how the universe in the set cover maps to the edges in the vertex cover, right? So now another observation is that we sort of the set cover sort of asks you to choose a collection of subsets from the input, right? So so the set cover problem says that now after we specify the all possible sets, right, as says and so on and so forth, right, then we sort of need to determine a subset of the input so that it covers all the universe, right? So this is the goal of the set cover. So now in order to do that, it seems intuitive to really map each set to a node in the graph, right? So that's maybe I can just label that as A, as B, as C, as D, as E, as F, right? So this is another intuitive mapping, right? So whenever I pick up a vertex A, that corresponds to picking up a set A in this in the input of the set to this it corresponds to pick up the set A in the set cover instance, right? So again, if I pick up F from the vertex cover instance, that should correspond to picking up the SF in the set cover instance, right? So this is the mapping I'm trying to build up, right? So what would be the consequence if I pick up A? If I pick up A, then I'm able to cover both the edge of E1 and E5, right? So I sort of want to deliver this intuition when I build up the set cover instance, right? So here, I do want to be able to articulate what I saw just now. So I let SA to be E1, E5, right? So basically, the semantically like this too, like I'm going to preserve all the information I need, right? So whenever I pick up an A, I'm going to be free of trouble for E1 and E5 because I'm able to cover both elements, right? So now we can sort of repeat the same process, right? So if I pick up the vertex cover B, then I'm able to cover the edges E5 and the edges E4, right? So then I can do let B to be E5, E4, right? And now this is F is a little bit more interesting instance, right? When I cover F, right, so then I'm able to cover quite a number of edges, right? So that includes E1, E2, E6, and then this is actually missing. Let's call this is E8, right? So E8, right? So basically for the F here, it's E1, E2, E6, E8. So this would really just correspond to the blue edges that I draw just now, right? So I can keep doing all these things for the rest of the sets. Now, then if I keep using this rule, then I manage to compile a vertex cover instance down to a set cover instance. Now, after I get this instance, then my solver is going to be happy because it can understand the instance from here, but you cannot understand the instance from the vertex cover. So now, after I feed into the solver, I will get a yes and no. And now, our hope is that if I'm able to find the set cover solution, then I'm able to find the vertex cover solution, right? So basically, intuitively, that really translates to a mathematical statement we want to prove, right? Claim if we do the transformation, as above, down as above, right? Then if like SI1, SI2, SIK is a set cover, then then I1, I2, IK is a vertex cover. Right. So I here are really just a bit can be somewhere between A to like what is the last one? A to F, right? So basically that says that if I'm able to find a set cover from the right hand side, and if I look at the corresponding nodes, then I should be able to find the vertex cover from the left hand side. And I wonder if and only if relationship, right? So if this is not a set cover, then this is then I1 up to I10, IK is also not a vertex cover, right? So sorry that my screen's frozen a bit. Let me just restart my screen. So let me repeat what am I doing here, right? So what we did just now is that we are given a vertex cover instance, we compile that down to a set cover instance, and then we want to claim that if the set cover instance, when it's fed into the solver, it outputs yes, then the vertex covers problem is also an yes instance. And if the set cover output a no, then the vertex cover is also a no instance. Like just recall what is yes. Yes means that there exists a set cover whose size is less than k, and the no means that there doesn't exist any set cover whose size is less than k, right? So basically we do want to be able to show that after we do this kind of transformation and reduction, well, our algorithm is actually correct, right? So by using this kind of logic, after I do the transformation, I split it into set cover, and the output is what we really want, right? In order to prove that, now we need this claim, right? So after this transformation, done using this approach, then then SI1, SI2 up to SIK is a set cover if and only if the corresponding set of vertices is a vertex cover, right? So this is really what we need, right? So to establish the sort of the equivalence between the vertex cover instance and set cover instance. Right. So now we want to prove one side, right? So if this is the first side, first part of the proof, right? First the direction, right? so now assume, right, Si1 up to Sik, Sik is a set cover, right? So that basically means that for any Ej such that for any Ej in the universe exists an Sij such that Ej is in Sij, right? So basically this is really just the definition of the set cover, right? So definition, so basically that means, let me go back to use this example, right? So if say that if I somehow determine that all these nodes forms all the subsets here form a vertex cover, that means that for whatever edge that appears in the universe, I'm able to find the set here that's actually covering this element or this set, right? So this is what I'm repeating here, right? So for any EI that's an element in the set cover and an edge in the vertex cover, right? We have two different interpretations for the same symbol. For any EJ that's in the universe, there always exists an Sij such that Ej is in Sij, right? So this is the definition of the set cover, right? Right. So that basically means that if I look at the graphs interpretation, right? So let's go back to the vertex cover problem. That means that for any Ej exists an Ij such that Ij is one end of Ej, right? This is basically basically it's really just the same statement, but I repeat the same statement for the vertex cover problem and I use the vertex cover language, right? So this is true really just because exactly because the way we do this reduction, right? So we guarantee this can happen, right? So but if this is true, then I1 up to Ik itself, it's a set cover, it's a vertex cover, right? So this is done, like we are done for the first direction, right? And then now we want to show the other directions, right? So only if direction. So that basically means that if Si1 up to Sik is not a vertex cover, not a set cover, then I1 up to Ik is not a vertex cover. So the proof direction is also similar, right? So if all the subsets here do not form a set cover, that means there's exists an edge such that Ej doesn't belong to any of the Sij for all Ij. Right. Right. So now again, if we just repeat the same thing, the same statement using the graph language, right? That basically means that that basically means that there exists an Ej such that it is not adjacent to any of I1 up to Ik, right? So that's actually the definition of that. That actually just directly means that I1 up to Ik, Ik is not a vertex cover. Right, so this is the logic here, right? So we somehow managed to establish the equivalence between these two instances, right? So that's the reason that we now finally managed to prove that if we translate the vertex cover problem using this manner, then we are guaranteed that the output to the set cover is yes, and if and only if the output to the vertex cover is yes, right? That's the second part of this lecture. So basically, in the first part of the lecture, we proved that the independent set and vertex cover are the same, are more or less the same, right? They reduce to each other. Now we sort of show that the vertex cover is easier than the set cover, right? So this is what we have so far. Right. So now let's switch back to the slides and move to the next reduction problem. Right. Our last topic today would be the constraint satisfaction problems. Sometimes people call it CSP, right? So as we can see, the set of problems that are here are much less natural than the packing and covering problems we have been talking about, because it seems that when we talk about the algorithms on the graphs, on the sets, there could be some very concrete examples, concrete real world examples that could benefit from the algorithm we design. And this is what people call the natural problems in the theoretical computer science, right? It naturally arises from the real world, right? So the CSP problem is not that natural. So it's not natural. So in the sense that's like a lot, maybe just throughout your career, right? So you won't be able to see a problem that's exactly in the format of the CSP. It's a highly artificial. It's something that human builds up. But on the other hand, this kind of problem is also the first, one of the first, actually it should be the very first NP hard problem that's discovered by human, right? So basically that means that some of the very earliest intractable, some of the earliest intractable algorithm problems are really just the CSP problem. So just now I wanted to say that this is the CSP problem is probably intractable problems, but then all of a sudden I realized that, well, P now at this moment P is really just very unlikely to be NP, and we don't have proof for that, right? So we can only say that this is with, but UCSP is the first candidate of the problem that is intractable. So now let's move to the definition of the CSP. In the CSP problem, right, so we have three central notions. One is the literal, second one is the clause, the third one would be the conjunctive normal form, right? Literal basically are really just the variables, right, x1 up to xn, such that each of the xi is a Boolean variable, right? Boolean variable basically means that it can either be true or false, right? So maybe in C++ or Java, you can really think true as 1, false as 0. So it's a binary or Boolean variable, right? So this is a literal. Each literal is either a variable, it's either a Boolean variable or it's negation, right? So negation basically means that if xi equal to 1, then the negation of xi would really just be 0, right? So we write things in this way. I get a little bit a bar that's on top of xi, right, to reflect that this is a negation, right? Similarly, if xi equal to 0, then the negation is xi equal to 1. Right? So this is the negation, and now this is the negation. And a Boolean variable or its negation is considered as a literal, right? So basically here says that either xi or xi bar, both of them are considered to be Boolean literal, right? So this is one of the smallest units in this in the CSP problem, right? After the literal, after we introduce the notion of literal, then we can use the literal to build up the clauses, right? So a clause is a disjunction of literals, right? So basically, when I say disjunction, you can really just think that as an OR function, right? So if I put x1 or x2 bar or x3, then basically this one is a clause, right? And after a clause, right, so basically we start with a set of literal and x1 up to x2, 3, 4, 5, right? And then I can pick up a subset of them and apply an OR function. Then all of a sudden this subset together with the OR function becomes a disjunction of literals, right? So, and conjunction normal form basically says that it's a formula, right? So this propositional formula, basically, if it's not comprehensible for you, then it's fine, right? After you see the example, it becomes very obvious what I'm referring to, right? So basically, this is a conjunction of clauses, right? So this will really just be in one example, right? So this is a clause, this is a literal, this is another clause. If I put AND operations for each of the to glue together each of the clauses, the entire thing is called the conjunction normal form. Right. So after I have the definition of these three layers of constructs, then I can talk about a problem that's called the set problem. Set problem basically means that given an CNF formula, does it have a satisfying true assignment, right? So what does that mean? That means that if I give you this, the phi the phi as an input, the entire formula as an input, are we able to find x1, x2, x3, x4 such that this formula evaluates to true, right? And then it turns out that the lecture slides claim that for this particular instance, it's true, is yes, right? So we are able to assign x1 equal to true, x2 equal to true, x3 equal to false, x4 x3 equal to false, x4 equal to false. I plug in all these assignments, and then you can check that then all of a sudden the phi evaluates to true, right? So so the SAT problem is exactly asking this one, right? So if I give you a conjunctive normal form, are you able to tell me whether there exists a feasible assignments of the variable so that the formula evaluates to true, right? Right. So now and also like after we introduce the set, and then there's also a notion of three set problem, right? Three set problem literally just means that it's a set problem, but we also restrict that the each clause contains exactly three literals, right? So if the problem is expressed in the three set way, then we sort of say that this problem is normalized, right? So the the reason we choose three set, right? So there's a magic number 3 here, right? So if we look into the two set, actually we are able to find an efficient algorithm for the two set. And what's very interesting is that when we move from two set to three set, all of a sudden the problems becomes much harder, and it's or in the sense that it becomes an NP complete problem, and very few people believes that this can be solved efficiently, right? So so we sort of want to understand the three set problem here, right? So this is actually consistent with what I was talking about, right? The set problem is hard. There's a very widely believed hypothesis saying that there shouldn't exist any polynomial time algorithm for this three set, right? And this hypothesis is also equivalent to our central claim that the P shouldn't be equal to NP, right? So we still haven't seen the definition of the NP, but then let's see. But then we are going to talk about that in the next 1 or 2 lectures, right? So our president, I don't know, I'm not going to comment about the elections. Yes. So now, after we introduce the three set problem, right? The task today is to show that the three set problem is easier than independent set. Right, so this is the theorem. We have a three set. I want to be able to show that it's easier than independent set, right? So again, let's just recall what's the syntax that's over here, right? We have a black box we want to construct. We have a procedure we want to construct, and then we also have a black box for solving the independent set ready, right? So we assume that we have access to a black box that can help us to solve the independent set, right? So now we start with the three set instances, and then we want to go through a little bit of transformation and then produce an independent set instance. And by looking at the output of the independent set instance, we are able to determine the solution to these three sets. Again, like this is both of the problems are decision problems, right? In the three set problem, the decision problem is very simple. Just ask the yes or no. Yes means that there exists a feasible solutions, whereas no means that there doesn't exist any feasible solutions for the three set instance, right? And so now let's proceed and to prove this theorem, right? So this theorem is actually quite interesting, right? So people start to I think this is the first time we start to see the notion of gadget, right? So let's assume that we start with the input phi, like this is our problem we want to solve, and the three set problem we want to solve. Now we want to compile this problem into an independent set problem,